Hello, everyone, and welcome to Perimeter Institute. I'm Lauren Hayward, and I'm a quantum physicist and teaching faculty member here at Perimeter, and I'm the co-host of our podcast, Conversations at the Perimeter. And I'm just thrilled to be co-hosting tonight as well. It's Dark Matter Night. Yeah. It's not just happening here. It's actually in a kind of superposition, happening in two places at once. And that's because tonight's event is simultaneously taking place at the Arthur B. McDonald Canadian Astroparticle Physics Research Institute in Kingston, Ontario. And my co-host, Mark Richardson, is there with a live studio audience. Mark, how are you, and how is the audience doing over there?
Thanks, Lauren. I think we're doing great. It's pretty warm in the room, but we're having a good night. So we're really thrilled to be entangled with you in sharing tonight's event. I'm Mark Richardson, everybody. I'm the Education and Outreach Officer at the McDonald Institute. We're a collection of scientists, universities, and research labs across Canada, uncovering some of the biggest mysteries of the universe by looking at some of its smallest things. And we are definitely thrilled to be both a virtual and a real pair of venues for tonight's exciting lineup. And what a lineup it is. We are very lucky to have talks from both Katie Mack at Perimeter and Ken Clark here at the McDonald Institute. And we have a special guest appearance from the Snow Lab group. They put together some extra content for Ken to include in his presentation. And so later in the evening, we're also going to have a few more opportunities. There's going to be a tour of the observatory if people want to head over there. It'll be raining, but anyway, I think there's still lots to see. And so yeah, lots of opportunities after tonight to check out other activities in these spaces. And so tonight I'd like to highlight that for me and Queen's University, our home is the lands of the Cataraqui, now Kingston. It's the traditional land of the Anishinaabe and the Haudenosaunee peoples and many Indigenous peoples before them. I am truly appreciative that we're all able to learn tonight, both from here and from our respective lands for those joining online and those at Perimeter. And I'm certainly appreciative of the fact that I have the opportunity to hang out with you tonight, Lauren.
Thanks, Mark. For us, Perimeter is just 2 decades old, but people on this land have been asking big questions about our universe for thousands of years. Looking at the night sky and understanding our place in the cosmos is a human constant throughout the ages. We are thankful to those who preceded us, and for those still present today and those who will follow, we will strive to act responsibly and collaboratively to carry forward the quest for knowledge for the betterment of all.
Yeah, and to all of you, I urge you to think of the connection that you have with the land around you and the gift that we have to learn wherever we are, including from the dark skies and longer nights above us, made even darker as yesterday was the new moon. And while I encourage you after tonight, maybe to even explore the website whos.land and learn about the past people who have lived where you live. And now, Lauren, back to you.
Thanks, Mark. Before I introduce our first speaker, let me say to those of you watching online around the world, please join us on social media. On Twitter, you can tag @Perimeter or @McDonaldInst, that's @McDonaldInst, because scientists from both institutes are online. And if you have a question for either speaker, you can ask online, and those questions will be relayed to me and Mark for the post-talk Q&A sessions. And now, it's my pleasure to introduce to you Dr. Katie Mack. Katie is a theoretical astrophysicist who holds the Hawking Chair in Cosmology and Science Communication here at Perimeter. She's the author of the book, The End of Everything, Astrophysically Speaking, and has written for a number of popular publications. On Twitter, you may already know her as @AstroKatie, where her smart and witty commentary on science has attracted hundreds of thousands of followers. And tonight, she's your first tour guide of the invisible universe. Please join me in welcoming Dr. Katie Mack.
Thank you so much. Thank you so much for coming out on this dark and spooky evening. We're going to be talking about dark matter, and dark matter is very close to my heart because it's one of the main things that I work on as a researcher. And I'll also talk about how it connects to our understanding of particle physics and the universe. So just to get us oriented here, hold on. We live in the Milky Way galaxy. This is a beautiful view you can get of the Milky Way in certain places. Because we are inside the galaxy, we can't see the whole thing, If we could, it would look something like this. This is our nearest neighbor large galaxy, the Andromeda Galaxy. So we live in this spiral galaxy with stars and gas and dust and black holes and all of that. And when we look out into the cosmos, we see galaxies everywhere. We see an amazing assortment of galaxies throughout the universe. But when we look at those galaxies, when we look at all that structure in the universe, that's really just window dressing. The majority of the universe is entirely invisible. So I'm going to be talking about one aspect of that, dark matter. And I like to use analogies and metaphors when I talk about dark matter and compare it to things that people have a personal connection to. So in this case, I will talk about the comparison between dark matter and the Force. So if you're familiar with Star Wars, then you know what the Force is what gives a Jedi his power. It's an energy field created by all living things. It surrounds us and penetrates us. It binds the galaxy together. So we can go through each of these characteristics of the Force and compare it to what we know about dark matter. Okay, let's start at the beginning. What gives a Jedi his power? Well, as far as we know, there's no connection between Jedi and dark matter. Also, of course, we know that not all Jedi are male, so that clearly doesn't work. What about the next bit? An energy field. So dark matter is a kind of matter, which means it's something that has mass. It has gravity. There is a connection between matter and energy, as we know from Einstein. So it does have energy. So you can think about it in those terms, but really it's a kind of matter. It's something that has mass, like the other particles that we deal with day to day. Next part, created by all living things. No, as far as we know, there's no connection between dark matter and life, whatever Philip Pullman says in his Dark Materials series. However, it is true that without dark matter, it would be very difficult for living things on Earth, at least, to exist because of its role in how galaxies formed in the very early universe. So that's one of the things that I'm studying is the connection between dark matter and galaxies in the early universe. But really, dark matter is something that helped galaxies to form in the first place in the universe. And I'll get into that a little bit more later. Surrounds us. Yes. So dark matter is something that seems to be around us all the time. It's something that galaxies are kind of embedded in. So you can imagine galaxies sort of inside these giant clouds or blobs of dark matter, where the galaxy is just a small piece and the dark matter cloud or blob, or we call them dark matter halos, are kind of engulfing the galaxies. Penetrates us. Yes. So it turns out that dark matter is, it's invisible, as far as we know, it's invisible because it doesn't interact with light, which means it doesn't interact with the electromagnetic force. So something that doesn't interact with light is invisible because light passes through it. It doesn't reflect or absorb light. It doesn't emit light. But if something's invisible, it's also untouchable. Because when you touch something, what's really happening there is the electrons in your hand are pushing against the electrons in that object, and that's the force that you're feeling. So if you don't have electromagnetism, if those electrons don't feel anything, then your hand would pass right through objects. And we think that dark matter is something that doesn't experience electromagnetism, and so it's something that can pass through other matter. So as far as we know, there is dark matter passing through this room right now. It passes through the Earth. It's going through us all. Binds the galaxy together. Yes. This is one of the ways that we first understood how dark matter works, is it's something that seems to be providing the extra gravity that keeps galaxies from spinning apart, and I'll talk about that more in a minute. Dark matter is something that brings other matter together and holds it together. So when you see a galaxy like this in the sky, you should imagine that it's really just a small part embedded in this sort of blob, this halo of dark matter. Okay, so I've just told you it's invisible. I've just told you we can't touch it. So how do we know it's there? How do we see it? So the main way that we learn about dark matter, about its existence in the universe, is by using the fact that it affects how things that do emit light move around. So in this video, you might not be able to see very well the person standing in the center, waving her arms around and moving that fire around in circles, but you could see that the fire is moving around in circles, and that's not something fire usually does. And you can see how quickly that fire is moving, which tells you something about how strong those arms must be, how fast that person must be moving those arms. And so you can tell that there's something causing that movement to occur. You can see the bright thing moving around. And that's one of the ways that we first learned about the existence of dark matter. So this person here, Vera Rubin, there are posters of her, I think, out in the atrium. She was one of the people who was studying how spiral galaxies rotate in the 1970s. And she was one of the people who gave us some of the most convincing evidence of dark matter's existence. She wasn't the only person working on this stuff. She wasn't the first person to hypothesize it, but she did play a large role in getting astronomers to understand that dark matter is a real thing that's out there. So she was looking at galaxies like this one, spiral galaxies, and she was looking at how they rotate. So spiral galaxies do rotate, not really like this, but the stars on the outside, the stars in the galaxy rotate around the central region. And by looking at how those stars are rotating around the central regions of the galaxy, you can learn something about the gravity that's holding them in, what it is that they're orbiting around. So for example, if you have something like a solar system or an asteroid belt, you have most of the matter concentrated at the center, and the objects orbiting around go more slowly in the center, go more quickly in the center, and more slowly toward the outside, because toward the center, they feel the gravity more strongly, they're closer in, and so they can go really quickly without flying away, and on the outside, they go more slowly. But when Vera Rubin and others looked at the way that stars moved around in galaxies, they saw something more like this, where in this animation, the stars at the center and the stars at the outside are actually moving the same speed. The ones on the outside take longer to get around because they have farther to go, but everything's moving at the same speed, which doesn't make sense if all the matter is concentrated in the center, or even if most of the matter is concentrated right there. And we can plot this out. This was one of the plots from her paper. So this is the rotational velocity as a function of the distance from the center of the galaxy. And what they found was that as far out as you could see stars, the stars were going about the same speed. Whereas if the matter really were concentrated where the light is concentrated at the center, then it should be dropping down something like this. And so it's kind of analogous to like, if you see a merry-go-round and there's a big kid pushing this merry-go-round, there's this little kid kind of holding on to the edge, and that merry-go-round goes really, really fast, then that kid, his arms are not strong enough to hold him in. He would just fly off into the dirt, right? But if it's going really fast and he's still sitting there, like he must have a little seatbelt or something holding him into that merry-go-round. And so dark matter seems to be that invisible force holding the stars within galaxies as they're moving around really, really quickly. And our understanding is that it's more concentrated in the center, and it gets less concentrated on the outside. It's kind of this spherical distribution-ish of matter. But you might ask if there's other evidence, because there are other ways to explain the orbits of stars around galaxies. And there is other evidence. There's a lot of other evidence in other areas of astrophysics and cosmology. I don't have time to go into all of them. I will tell you something about gravitational lensing, though. So there's a demo of this out in the atrium earlier. This is a sort of cartoon illustration of Einstein's theory of relativity, of general relativity, his theory of gravity. So the idea there is that massive objects kind of make dents in space. They kind of bend space around them. Now, this is a 2D representation. Really, we live in 3 spatial dimensions. So you have to imagine, instead of making a dent like that, what's really happening is that massive objects are kind of pulling space toward them in all directions. It's harder to illustrate on the graph, but the idea is that massive objects curve space, and then other objects, if they're moving around nearby, respond to the curvature of the space. They move through the space along its curvature. So if you have a massive object and another object moving past, then the path of that object will be curved because the space is curving due to the presence of that mass. And if you, instead of having a massive object moving past, if you just sort of shine light past something massive, then the light also follows the curve of space. And so you end up with light curving around in that curved space as well. And the cool thing about gravitational lensing is it doesn't care what the matter is made of. If there's matter that's bending space, then space is bent and everything responds to that, even if that matter is invisible, even if it doesn't interact with light. So there's a cool animation of this made by a science fiction author I like a lot, Greg Egan. He writes these extremely nerdy books about science fiction. But anyway, he also does a whole lot of sort of physics illustrations and stuff in his free time. And he made this illustration of what it looks like if a big invisible object moves past a field of stars. So imagine, an invisible object is kind of moving between you and some background stars or galaxies or whatever. Now, you won't be able to see the object, but you'll know it's there. Okay, so when I start the animation, you can see that the background is being warped by the presence of this mass. And as this mass moves along, it's distorting the images of those background objects because the space it's bending the space so much that the light from those background objects is being warped. You're getting multiple images of some of these background objects. You're getting these rings if the alignment is just right. And that's called gravitational lensing. And we actually see that in the sky all the time. There's some amazing images of this. So, for example, this is one from JWST that just came out a few weeks ago. So this is a cluster of galaxies here, and it's bending the space, and you can see these arcs where the background galaxies are distorted by the bending of that space. And if you actually counted up how much mass was in all the stuff that's shining, it's not enough to create that much bending. Right? So when you look at an image of gravitational lensing, it's measuring all of the mass, and most of that mass is invisible mass. And we have tons of images of these where you have galaxies or clusters of galaxies, and they have these really amazing distortions of these background galaxies and multiple images of background galaxies. And if the alignment is really good, you get these giant arcs. And if it's really perfect, you can get a whole circle. It's called an Einstein ring. Sometimes you get a happy face. And in all of these cases, just by looking at the placement and distribution of those arcs and those distortions, you're really weighing the total amount of matter there. And you find that most of it is stuff you cannot see. Okay, so then what is it? We don't know. The usual starting point is something called weakly interacting massive particles. Okay. What we're saying here, so weakly means it interacts with other matter either weakly or not at all. So weakly being either sort of feebly or just via the weak nuclear force. There are a couple of different ways to interpret that. But we haven't seen any interactions with other matter. I'll talk more about that in a bit. Massive in the sense just that it has mass, not that it's really heavy. And particle in the sense that it acts like a collection of particles. It acts like a collection of particles that just don't have electromagnetism. So we usually abbreviate this to WIMP. The name came about back in the day when the other major alternative was massive compact halo objects, MACHOs. So what is a WIMP? Well, we know we have a bunch of particles in the standard model of particle physics. So this is the standard model of particle physics. We actually found a new one recently, the Higgs boson, there. So these are the particles, these are all the particles we've ever detected in a particle detector in an experiment of any kind. Okay, so the blue here, these are the quarks. They come in 6 different flavors, up, down, charm, strange, top, bottom. They were named in the 60s and 70s. The quarks are the things that make up the protons and the neutrons, the particles that sit in the centers of atoms. So protons are made of 2 up quarks and a down quark. Neutrons, 2 down quarks and an up quark. Then in the green, these are the leptons. There's the neutrinos, which are these sort of ghostly particles that come from the sun and other stars. Then there's the electron and its heavier cousins, the muon and the tau. The electron is the thing that goes around the atom. Usually it's depicted as a kind of orbit, but when you get into more physics, you find that it's not really orbiting. It's kind of a cloud of electronness around the center of the atom. And then in the red here, these are the gauge bosons, which are the force carriers. They're the particles that mediate the forces of nature. So there's the photon that does the electromagnetism. So photons are responsible not just for light, but for electromagnetic interactions. There's the gluon. That's the thing that kind of holds everything together inside the nucleus. It's the mediator of the strong nuclear force. And then the W and the Z bosons have to do with the weak nuclear force. So they have to do with things like radioactive decay, the weak nuclear interaction. Okay, so which of these could be the dark matter? So we could look at what the properties we need to have for dark matter are. So we need it to be massive. It has to have some mass. So that rules out the massless particles in this model. It needs to be long-lived in the sense that it can't be decaying into other particles. It needs to be, something that holds its own. So that gets rid of the ones that have short decay lifetimes. It has to have no electric charge because we already said it doesn't interact with light. It doesn't interact with electromagnetism. So that rules out the electron and the remaining 2 quarks. And then the final thing is it has to be slow-moving in the sense that if it's just zipping through the universe all the time really fast, it doesn't collect into those halos. It doesn't bring matter together. So it's called cold dark matter is the usual paradigm. It has to be slow-moving. It has to be kind of sluggish. And that rules out all of the neutrinos that we know about. So we're left with a bit of a quandary, which is that we have this standard model particle physics. It's everything we've ever seen, touched, interacted with, detected, and it's none of those. And that means that whatever it is, it has to be something that's in addition to the standard model. It may be one thing, it might be several things, but it's something beyond the standard model particle physics, which is part of why it's exciting, because if we figure out what it is, then we've automatically improved our understanding of particle physics. Okay, so how do we find it? Now, there are a number of different things that we can look for, and I'll kind of talk through a few of those briefly, and then Ken Clark will go through in more detail the detection that he and his colleagues are working on. So the problem is that, I said it's sort of untouchable. That means that when dark matter and regular matter kind of go past each other, they tend not to interact. But there's a chance that every once in a while, there will be some interaction between dark matter and regular matter. Maybe they have some interaction via the weak nuclear force. Maybe it's really, really rare, so much that it doesn't show up in our sort of astrophysical observations. In which case, there's got to be some kind of interaction that could happen between these particles, right? And so we usually draw interactions kind of like this. So if you want to look for dark matter through direct detection, you kind of read the diagram this way and wait for a dark matter particle to bump into a regular matter particle, and the regular matter particle comes out. So what we'd actually see, since we can't see the dark matter, is we'd see a regular matter particle bounce off something invisible or be bumped by something invisible. That's kind of what they're looking for with direct detection. Then you can think of maybe reading this diagram a different way, right? So if there's some interaction that connects these things, maybe it connects them in a different way. Maybe you can have a situation where 2 dark matter particles come together, annihilate with each other, and regular matter comes out the other side. And this is something that some theories of dark matter have in them, that dark matter can annihilate with other dark matter and create regular matter. And that gives us the option of indirect detection, which is where we look into the sky and we look for the sudden appearance of high energy particles from places where we don't expect them to come. Because when this interaction happens, when the dark matter turns into regular matter, what we would see is just regular matter appearing, high energy particles or sometimes gamma rays because of the conversion of high energy particles into gamma rays. But if that can happen, then if it can happen this way, then you can expect that it should also be able to happen the other way. So regular matter particles should be able to come together and create dark matter. And that's the idea behind the production method, where we're looking for the production of dark matter in particle colliders. And so what we would see there is that we would see that we'd smash our particles together, and they would seem to disappear. That there'd be missing energy in the collision. So let's kind of sum up where we're at with all those things. So direct detection, it's inconclusive. Hopefully Ken Clark will tell you a little bit more about this, but there have been a few hints, but so far it was nothing really convincing. Indirect detection, also inconclusive. We've seen a few places where there's extra stuff coming from things in the sky we didn't expect extra stuff to come from, but there could just be astrophysics we don't understand. And then production, there's been no signal. We haven't seen anything in those colliders. However, the astrophysical evidence for dark matter is really very, very strong in a lot of different regimes. And so where we sit is this. We can make a pie chart of what the universe is made of, okay? And we can do this by studying the amount of dark matter we see out there, the evolution of the cosmos, a lot of different parts of cosmology. And it tells us that about 27% of the universe is dark matter. It tells us that about 68% of the universe is dark energy, which I didn't get into. It acts kind of very differently from dark matter, but it's most of what the universe is made of. And then there's this little 5% slice that I've labeled atoms here. And that contains the entire standard model of particle physics. Everything we've ever seen, touched, interacted with, detected in an experiment. And that means we have this fantastic opportunity by studying dark matter to massively increase our understanding of the universe and also massively increase our understanding of particle physics. So I'm out of time, I will leave it there, and I'll take some questions and then we'll move over to Ken's talk. Thank you.
Thank you so much, Katie, for that fascinating talk. As you said, we're going to have a Q&A session now. And so for those here in person at Perimeter, you can find your way to the microphone in the aisle if you'd like to ask a question. For those at McDonald Institute, you can raise your hand and someone will bring a microphone to you. And we're going to start with a question that was sent in online. So I really like this one because I think it might have a tie-in with your book, Katie, The End of Everything. So the question is, what do you think might happen to all the dark matter at the end of the universe?
Oh, that's an interesting question. What will happen to dark matter at the end of the universe? So I actually worked for a little while with a student thinking about this question about how dark matter would sort of evolve into the far, far future and what we would see. And my understanding, I mean, we don't know what dark matter is, so we can't be sure about this. But if dark matter is something that annihilates, then over time, that dark matter in halos would annihilate and turn into regular particles, turn into radiation through a cascade, and eventually sort of spread its energy out through the universe, just as everything else will. So as the universe evolves, you know, the stars will burn out, the galaxies will sort of fade, black holes will evaporate, and dark matter over time, the amount of dark matter will decrease if it is something that annihilates, because then it'll turn slowly into a sea of high energy particles and radiation. So that's our best guess at the moment for what dark matter will do.
Amazing, thanks. Let me just encourage our live audience again. If you'd like to ask a question, please make your way to the microphone. Mark, do we have any questions from your audience over there? I'm seeing you. Okay, maybe I'll go to, oh, we have someone approaching our microphone here in person. So please go ahead, introduce yourself and ask your question.
Hey, I'm Justin. Earlier you mentioned that there are certain fundamental particles that are short-lived and decompose. What I'm wondering is, what do they decompose into? Is it just energy, or how are they short-lived in that way?
Yeah, that's a great question. So it depends on the particle. So in general, what they'll do is they'll decay into a lighter particle that they have some interaction with. There are other kinds of interactions that can happen. They can decay into different kinds of channels. So for example, when the Higgs boson was detected at the Large Hadron Collider, it wasn't the Higgs boson that they saw, it was the decay products of the Higgs boson that they saw. And they saw different kinds of decay products. So they saw, you know, gamma rays, they saw some quarks and things like that. In the case of the quarks themselves were also not really stable. They saw other things that came out of that. So it depends on the particle and sort of what its interactions are with the other particles.
So pretty much what you're saying is that it will keep on decaying until it reaches a more stable state?
Yeah, so it'll decay until it gets to something that doesn't decay. So generally, so we don't think that protons decay at any very long, or for a very long time at least. And so a lot of particles, so like if you leave a neutron alone long enough, it'll decay into a proton. There's yeah, so it'll just it'll decay into whatever the sort of most stable part of that part of the standard model is.
Thank you.
Sure.
Great.
Hi, my name's Brenna. I have 3 questions. Number 1, you were talking about the lifespan of dark matter. Approximately how long is it?
So the lifespan of dark matter. So it depends on the kind. So it depends on the kind of dark matter. So because we don't know what it is, we don't know how long it'll last. If it's a kind of dark matter that annihilates with itself, because so some kinds of particles theoretically can be their own antiparticle, which is kind of weird, but that's apparently something that dark matter might be able to do. If that's the case, then when the 2 dark matter particles come together, they would annihilate, but otherwise they're stable. So when I mentioned that the dark matter would, annihilate eventually in the distant future of the universe and decay away, then what's happening there is it's because there's concentrations of dark matter where you can have that annihilation happening. There are other models of dark matter where it does legitimately decay into something else. So some models of dark matter have it decaying into like X-rays and through some process. And so it varies by what the dark matter is.
Okay. My second question is if there are different types of dark matter. I know you were talking about there being kind of roughly 2, but would that have anything to do with how they bounce off of each other as well?
So we don't know if dark matter is one kind of thing or a whole bunch of different kinds of things. In the diagrams, I was kind of trying to depict a kind of dark matter where it's its own antiparticle, so it sort of can annihilate with itself. But there are other ideas where you have a whole range of different kinds of dark matter that are kind of at different densities throughout the universe. There are some kinds of dark matter theories where you have 2 different types of dark matter that interact with each other in certain ways. So it really varies. And we don't know if it's more unreasonable to hypothesize a single kind of particle that we can't see or a whole zoo of particles that we can't see. Like those are, depending on who you ask, those are sort of equally extravagant hypotheses.
Mm-hmm. And my last question is, if the universe can grow, will the amount of dark matter also slowly get larger?
So as far as we know, the universe, the growth of the universe, the expansion of the universe is really just the sort of empty space getting bigger, and all of the stuff in the universe, it's the same amount of stuff. So it's just distributed over a much larger space in that scenario. So probably not. Probably the dark matter is just diffusing just like everything else.
Okay, thanks.
Great. And next
Katie,
we have a
question on our end as well.
Yes, we have a question from the McDonald Institute. So Mark, over to you.
Is there a relationship between black holes and dark matter?
That's a great question too. So there are some hypotheses for dark matter where it's made of tiny black holes. The idea is that there are some scenarios in which tiny black holes are formed in the very early universe. These are called primordial black holes. And if they're not so tiny that they would evaporate completely by now, then they might be around. And if they're around, then depending on their mass, they might act a lot like the kind of dark matter we usually think of, just particles that don't interact that much with other things. If they're too big, then they can mess up galaxies. If they're too small, they evaporate. But there's a middle ground where they don't do a whole lot dynamically. They don't mess up galaxies too much. And they also don't evaporate. And they don't pull in a lot of matter because they're just little. And in that scenario, in that sort of little mass range, kind of somewhere around an Earth mass where the size of the black hole would be like this big, we wouldn't be able to necessarily tell them apart from other kinds of other ideas about dark matter. So it's possible. It's not the favorite idea for what dark matter is made of, but we don't know for sure.
Great, thanks, Katie. I think we're going to take one more question, so let's take one more from our live studio audience here.
Hi, I'm Madeline.
Hi.
Is there any particular quantum mechanical aspects of dark matter that's special? For example, symmetries, any hidden symmetries or something like that?
Yeah, it's a great question. It's another one I have to answer with, because we don't know what it's made of, we don't really know what the particle properties are. But there are some really interesting possibilities for dark matter where the quantum mechanical behavior of dark matter is really important. So for example, some of my colleagues here work on an idea called fuzzy dark matter or ultralight dark matter, which is a kind of dark matter particle that's so light, the mass is so small that the wavelength of it, so every particle has kind of a wavelength depending on its mass, where it can't be really localized in one spot. And if it's a small enough mass, then the wavelength is so long that it can't fit into a galaxy. And so there's a kind of these ultralight dark matter models. The quantum mechanical aspect of that particle is really important, how it interacts, really important to how it deals with galaxies. And so it can create things like interference fringes within galaxies where you get sort of variations in the mass, little speckles in the galaxy because of the interference of the dark matter with itself, which is very cool.
Thank you so much.
Thank you.
Okay, thank you so much for all of those great questions. I want to thank our audience here at Perimeter in Waterloo, our audience in Kingston, and our online audience for some really great questions. Thank you, Katie, for your amazing talk and for all of those insights that you've shared. Let's all thank Katie again. Thank you. And now let's hand things over to our colleagues at the McDonald Institute. Over to you, Mark.
Thanks, Lauren. It is my honor now to introduce the next tour guide for our dark evening on heavy matters. Professor Ken Clark is an associate professor at the McDonald Institute, located here at Queen's University, and a research scientist at Triumph. Ken works with the Pacific Ocean Neutrino Experiment off the coast of British Columbia, the PICO collaboration, mostly at Snow Lab in Sudbury, and he is the Canadian spokesperson for the scintillating bubble chamber. And tonight he's going to tell us a little bit more about how we might go about looking for this elusive dark matter. Let me just start sharing his slides. Give me a moment.
Got to say, I'm in a pretty good position here, having had such a great intro to how this is the whole situation. It's going to make it much easier to give this talk. Okay, so the talk that I've been, that I'm giving is how we're looking. By that I mean, I just realized, by that I mean dark matter, how we're looking for it, not like we're looking good to dark matter. That's not what I meant by that title. But so how we're actually searching for it and what we're going to do. And the reason for that being, I am an experimentalist. I have spent quite a bit of time looking for dark matter, maybe more than I want to admit. And we just had this really great introduction by Professor Mack at Perimeter about what it is, or what we think it might be, and why we think it exists. And so it was a lot of, we don't know a whole lot about it. So we need to find more. And it's obviously challenging. We heard a lot about how challenging it's going to be. But instead of just kind of giving up and crying, we're going to try to start by making things, looking for different ways in which that we can detect it. So we don't know very much about dark matter. We don't really know how, we don't know what it is. As we heard, we don't know how it's going to interact. So we're going to search widely. We're going to open our field and use a number of different methods to try and find out what it is. So in doing that, the colloquial way of thinking of it, there's basically three kind of categories we're going to use. So those are, we can make it. So that's one of the things that we can do. We could break it. And obviously, this is going to be another one that rhymes. We can shake it. Also, side note, this is the high quality of animation that's going to occur throughout my slides. So buckle up. I'll expect Pixar to be calling. But these are the three kind of general methods that we're going to use. We can make, we can break, and we can shake. And I'm going to go through those one by one and try and give an example and talk about how we're going to use it to find each one of them. So the first one is make. This is kind of the one that everybody thinks of when they think particle physicists. What we're going to do is we're going to take something that we know, particles that we know, electrons, protons, neutrons, maybe some light atoms, things like that. We're going to get them going real, real fast, and we're going to smash them together. And we're just going to see what comes out of that. There is some, this is more than just fun and a fun idea. There is some logic behind this. What we can do is we're providing kind of all the building blocks in terms of the energy that we need. And so if we provide all of this energy in a limited space, then essentially anything that can be produced eventually be produced. In terms of, if we keep running this long enough, we should have all the possibilities for things that could come out. And that includes dark matter. So what we can do from my high quality slides here, we take these particles we know, we smash them together, and we control where they smash together. Where they smash together, we have a detector that is incredibly sensitive and incredibly complicated, and is there to kind of find out what is coming out of that collision. So I just want to take a brief second to talk about this plot. So essentially with this plot, what you're doing is, this is one of the events from the ATLAS detector at CERN. So what you're seeing is you're essentially looking down the collision point. So the two particles that we just saw expertly animated going around, are coming into the screen and out of the screen. And they've met at the screen. And what we're doing is we're seeing the spray of particles that's all coming out. So you can see there's different layers of detectors, and they detect different qualities about the particles, but we're using those to detect all the particles. So this is the kind of thing that we're doing. So it has advantages and disadvantages. One of the disadvantages, obviously, it's kind of difficult to produce the energies that we need. If you have a few $1 billion lying around, you could start building one of these accelerators and trying to figure out if you can do it on your own. And the other disadvantage is that the analysis is really challenging. I'm going to get into a little bit of that in the next slide. But there is precedent for doing things this way. I mean, this is how, you know, the Higgs was recently found. We just kept smashing things together and looking at what came out, and then eventually you can identify that there's something there. Excuse me. So I wanted to talk just a little bit about what we're doing, because all of you just heard this great talk about how rare it is that these particles interact, and you're thinking to yourself, okay, fine, Professor Clark, I kind of believe you, you can smash things together and make them, but how could you possibly detect them? That is the trick to the whole thing. So you can't detect them. All you can do is realize that something is missing from your collision, and that's what's shown in this here. You can see that on the picture going off to the right, there's a couple of events, there's things going on. It's hard to read these plots, but they gave the nice cones showing what's happening. So there's something happening that's going on there, but there's nothing coming off to the left. And if this was truly a system that had no left or right balance coming in, it has to come out. There are all sorts of conservation laws that say this has to be balanced. So there has to be something coming out along this dotted line. And so that's the way that they actually look for these events, is to say, we can put together, piece together everything that happened from the shrapnel. There should have been something over here, and that's missing. And is there some way that we can, you know, get a bunch of events that are missing and collect them and then identify that there's dark matter? So that's the kind of make it strategy that's there. The break strategy, we just heard actually in the really good previous talk about self-annihilating dark matter. So there is some chance that we kind of do the opposite of the make strategy. We take particles we don't know, they collide together, we don't cause it, but they collide together, and they turn into something that we do know. So in my great animation here, we have our two dark matter particles come together, they annihilate, they go away, and they turn into something that we understand. So this is pretty convenient in that now we have something that we can actually detect potentially, that's come out of this, and that we can do that. But to do that, of course, we need a detector. So I am showing here one example of a detector that could be used to do something like this, a biased example, as all of my examples are in this talk, by a project that I actually worked on. I'm showing the ice cube detector. So in the little model of planet Earth here, in the South Pole, we have a detector that looks for neutrinos. So if there is some chance that all of these dark matter particles, they come together and they annihilate, and then they produce neutrinos, we can then detect those, and we can use those to go backwards and figure out there was dark matter there. So this is good in that we no longer need the billions of dollars to make all these accelerators. That's taken care of for us. But identifying these things is not simple, because there's coming in from everywhere all the time. And so what we really want to do is be able to have some way of saying that yeah, that looks like dark matter. And that was touched on as well. What we'll do is we'll look for places where we think there would be a collection of dark matter. So since we know dark matter interacts gravitationally, all the big heavy stuff we saw in the previous talk, the really nice illustration of the curvature of space-time, and then there's a heavy thing in the middle. The dark matter can actually get trapped down there. So you can think of all the kind of heavy stuff that's around. You can have this kind of puddle of dark matter in the middle of it. And that gives a really nice place for dark matter to annihilate and then turn into something that we can see. And the sun is pretty heavy, so we could use the sun. We can see if we saw a whole lot of events coming directly from the sun that we didn't understand, then we would be able to say, hey, maybe there's something going on. Maybe dark matter is annihilating. But do need to be able to point back to do that. So I just wanted to give a brief illustration because IceCube has some great illustrations. This is a cartoon of the IceCube detector, just showing that in the ice at the South Pole, there's all these light sensors installed that can actually see the light and see from the interactions. So what we expect to see is a particle coming in, a neutrino. It hits something and turns into a different particle that we know, but that particle is going faster than the speed of light in ice. So it's producing light along its path, and we use that light to be able to trace backwards to where it came from. So you can see in this event, particularly, you can trace back along that line and say, yeah, we know exactly where that neutrino is coming from. And that would give us to say, hey, all of these neutrinos are coming from the sun. There's something going on there. Maybe we should look at it, and maybe it's dark matter. So that covers the make and break strategies. So the final one is the shake strategy, which is, to be quite honest, kind of the weakest one in the rhyming triplet here. What we're going to do there is we're going to have the dark matter particle come in and hit something that we understand, usually a nucleus. So the dark matter particle comes in, hits a nucleus. That nucleus bounces back just a little bit. So this is just balls on a pool table, essentially. And when that nucleus bounces backwards a bit, we're going to be able to use that to find out that dark matter is happening. So illustration time, boom, dark matter particle goes away, nucleus bounced backwards just a tiny bit. This gives us the signal that we can look for. So that's the shake strategy. So again, the signal's happening all the time. As we heard, dark matter is streaming through us and all of that all the time. So that's good, but interactions are really rare by definition. So we can kind of get over that. If we put a lot of targets in its way, then we're increasing the odds of this happening, obviously. Well, not increasing the odds, but increasing the odds that we actually see one of these events. So that's okay, but there's very little energy there. You can imagine when you're just thinking of energy and thinking of things to detect, the movement of a nucleus is not something that's easy to find. So I was trying to think desperately of analogies for this. What I kind of came up with was comparing it to earthquakes. I mean, not my best analogy, probably not my worst though. You can talk to my student. So what we're trying to detect in an earthquake, you're trying to detect the movement of tectonic plates, right? These big things sliding against each other. For dark matter, we're trying to detect this nucleus going backwards, and that's it. So, the most simple, the most basic way to detect them. With earthquakes, we've all seen this rolling sheet of paper and the pen on it. So when the pen shakes, you actually get this recorded. With dark matter, it's a little more complicated. You might have to have some, superconducting things operating down at minus 270 C. It's a little bit harder. But here's the really big problem: the energy. So I had to look this up, but a magnitude 0 earthquake, I learned a lot about earthquakes the past few days, gives off 63,000 joules of energy. Now, a magnitude 0 is not something you will ever feel. It's defined as being an earthquake at which 100 kilometers away, a particle moves 1 micron. So it's not very much, but it still gives you 63,000 joules. When we're looking for this nucleus recoiling, that gives you 0.00000000000000000001 joules, 10 to the minus 16 joules to try to detect. This is not very much. And then, of course, I had to put in this last row, just, earthquakes definitely exist. I don't want to give people the impression that I don't think earthquakes exist. Dark matter, the jury's out on that one. So what is that quantity of energy? What does it mean? Again, trying to find some analogies. This one I like slightly more. If you take an average bacterium, no such a thing existed, but apparently an average bacterium weighs this, 10 to the minus 10 grams. So convert that to kilograms, you get into here. If you figure out kinetic energy, half mv squared, all the students here, following along wonderfully. So how fast would this thing have to be moving in order to deposit the energy that we're looking for from that dark matter signal? Turns out, you go through the math, it works out to 0.02 meters per second, or roughly 0.1 kilometer per hour. That's pretty slow. I have a 2-year-old who likes to go on walks around neighborhoods. I know slow, and this is very slow. So there is not much energy that's being deposited here. What we're going to need is really fancy detection schemes to be able to figure out if we can find this amount of energy. So I'm going to talk about 3 examples, again, completely biased by my experience. But the first example is we could use noble elements. Now, noble elements have this great property that when there's deposits of energy, small deposits of energy there, they produce light. They scintillate. So we can use that. We can say that we can't really detect this nucleus moving backwards very well, but we can really detect light very well. So as long as this is producing light, then we can do this. We can use that to try to find out what's going on. So here's our animation. He comes in, produces light, and that's the signal that we're looking for. The example that I'm going to use here is the LZ detector, or the LZ detector, I guess, since they're not based in Canada or the UK. So this is their version of that detector. Inside this nice, clean, white Teflon sheet is just basically a bucket of xenon. Xenon is one of the noble elements. It makes a great target for a lot of reasons. Now, all along the bottom here, oh, I do have the mouse, nice. All along the bottom here, these are what are called photomultiplier tubes. So they take in like even just single photons and turn it into an electrical signal that we can detect. So you take your bucket of xenon, you put all these photomultiplier tubes on the bottom and also on the top for a slightly different reason. But you do that, and then you can detect the light. So by doing so, we've changed this little nuclear recoil into light. We know how to detect light. Everything's good. And then LZ can go on and do their detections. Another thing we could do is we could use really, really cold detectors. I mean, very cold. As I said earlier, operating at basically almost minus 273 Celsius. So extremely cold detectors. What we're looking for there is that same particle to come in and cause that nucleus to recoil. But then two things will happen. One is that as the nucleus recoils, some of the electrons, or some of the electron cloud, is going to be left behind. So it's going to be separated from the nucleus. And we know how to detect electrons, or electron clouds. We know how to do that very well, so we can use that. The other thing that we can do is, because this is so cold, and because you have a really nice lattice of particles in here, that little recoil is going to cause a vibration in the lattice. And that vibration to change the temperature of this very slightly. So if you have an extremely sensitive device that measures temperature, you'll be able to see not only that there's been electrons produced, but also that the temperature went up just a little tiny bit. So that's the signal that we're looking for here. So your particle comes in, produces electrons, you pull those down, you make those go to your electron sensor, and it causes this vibration, which you would detect on the detector as well. The example here, again, my experience biased, is the CDMS, the cryogenic dark matter search. So this is a picture of one of their detectors. It's like hockey puck size, maybe two hockey pucks on top of each other, of solid germanium. So a very clean, pure material. And that's going to be able to give us this reaction. They instrument one side with these electron collectors, and they instrument the other side with extremely sensitive temperature detectors. And doing that, you're able to see the signal that's come from the dark matter coming in. The last example I'm going to give is you can use superheated liquids. So if you have a liquid and you manage to have it in a container and take it above its boiling point, that means that any small deposit of energy can actually cause that to boil. So this is a great way of kind of amplifying what's going on. So your dark matter particle comes in, causes this little boiling, and then the boiling expands as your detector boils. We watch the detector, we look for these interactions, we see what's going on, we can also listen to it. And so this gives us another way that that little deposit, that tiny recoil, has been changed into something we know what to do with. So example here is the Pico detector, which I also work on. This is the most recent generation of the Pico detector, Pico 40. You keep your superheated liquid in the center part here between two very clean, very expensive fused silica jars. And those are so smooth and so clean that you're able to raise the temperature of your liquid up above its boiling point. And it will just sit there and wait for one of these particles to come in and give you a nice deposit of energy. Not shown here, although they will be shown in a little bit later, are the cameras that we use to watch it, the microphones that we use to listen to it, all of the things to do the detection itself. This is just the internal guts, and I just use it because it's just a really pretty picture. We still have kind of a big problem. I told you that this situation that we have going on, right? Super simple, nucleus goes backwards, tough to detect, but maybe we know how to do that. I might have convinced you. But what we really have is something that looks more like this. There's stuff going on all the time, and you have to sort out what's happening to try to figure out what's going on with this, and to distinguish all of the other things happening in your detector from the one recoil that you want, the one nucleus movement that you want that was caused by dark matter. Collaborations do this in very different ways. They work very hard in order to do this. I've shown 3 examples that correspond to the 3 examples that I gave earlier. In the top left here is what you get if you have like a noble detector. Basically what you do is you look for the scintillation that happens when you first have an interaction, and then you take those electrons that got forgotten, you force them to come up and make them scintillate too, and you look at the amount of light produced by each of those reactions. And the different ways of causing an energy deposit produce different ratios of that. So that gives you a way to distinguish between what you want and what you don't want, which is a lot of stuff. For cryogenic detectors, you already have two methods of seeing things. You have the electrons, you have the heat. Balance those two and say that the way that we want, if we have a real nucleus moving backwards, it looks different in those two ratios. And then if you have a superheated droplet detector, like the pico detector, or superheated liquid detector, like pico detector, I back to about 15 years ago there, and mistakenly, you can actually listen to it. And it turns out the different ways of generating this sound actually cause, they are generating this nucleus movement sound different. And so you can separate out that way. And this is the part that really kind of blows my mind. Yes, it's hard to detect things. Yes, you know, looking for a nucleus moving just seems like it should be science fiction and not possible. But being able to separate out why that's happening is pretty incredible to me. So collaborations spend a lot of time trying to do this. So we would say if only there's somewhere that we could go, that we could put our experiments, that we wouldn't have to deal with some of those backgrounds. So clearly I'm leading into the next part of the talk here, which is SNOLAB. So SNOLAB is a facility that it's deep underground science facility. It's somewhere that I'm familiar with, having worked there for a long time and actually having been worked at the SNOLAB facility for a year and a half in my career. So where is it? It's just a short 4-hour beautiful drive north of Toronto. You go up just outside of Sudbury. There's the SNOLAB is housed. You can see that in this expanded picture here, this is the actual SNOLAB building itself, where the scientists hang out and do science, I guess, while they're there. The only thing you can really see of the mine is this green kind of tower here. That's the head frame. So that's the top of the mine shaft that takes you the 2 kilometers underground that you have to get. I will say this picture does not show the best side of Sudbury, I think. It really is beautiful up there. This great kind of Canadian Shield area and lots of lakes and not just this. So SNOLAB it's a big thing. There's like 1,000 users, a bunch of institutions across many countries, which is good. And we go underground. We do all of this work to get down there for this reason. I told you, we have to distinguish all of these events. Well, if we could not have some of these other events, even better. So what happens is all the time we're being bombarded by cosmic radiation. There's cosmic rays coming in, they interact in the atmosphere, they produce muons and they produce electrons and neutrinos and they produce a whole bunch of things. Those are streaming down and streaming through us all the time. That's not a big deal for us as people. For our experiments, it is fatal. You could not run any of these experiments on the surface. So by going 2 kilometers under the Canadian Shield, you get this great shield, not to be too repetitive, and you lose a factor of 50 million on all these events. So you have a dramatic reduction in the backgrounds. But going underground itself is not super simple. SNOLAB provided a video here, which is really dark and mostly black, of people going underground. So this is people on the cage, which is what it's called when we all cram together with the miners and go underground. You can see everybody in their, well, you can see everybody in their mine gear, packed together in this little room going down. It takes about 5 minutes or so if you get a direct shot down to the 2 kilometer level. So here you can see the levels that are going by. They happen about every 200 feet or so. There's another drift that has been mined out by the mine. This is all still an active mine, by the way, so there's lots of miners and it's super fun to be able to go there. So our team has arrived at the 2 kilometer level, and now they have to walk through the drift, which has been mined out previously, so just the tunnel underground. And you can see them walking through with their headlamps on and all their safety gear through the actual mine itself. They finally get to SNOLAB, this is just outside of the facility, and they come into the facility, so that's where this video ends. We're walking into the facility itself. So that's kind of the process of getting down and going into SNOLAB. And so one of the other things, in addition to just the shielding, I went and, on a little rant about bacterium at some point, which you probably stayed awake for, but this is saying that any little thing that's around, any dirt that's around, anything like that can really cause serious problems with our detectors. So the way the SNOLAB was constructed, the entire facility is a class 2000 clean room. You can see it looks really clean, but what exactly does class 2000 mean? So these are the illustrations that the SNOLAB uses. In the mine, when you're walking through the mine underground, if you take 1 cubic foot of air, there are about 10 million particles that are above half a micron in size. So if you were to count up all the particles bigger than half a micron, you would get to 10 million in a cubic foot. I know the mixture of units bothers me too, but there's nothing we can do. That's just the way these things are judged. So that's if you're just walking through the mine. In your home, I think this is a little bit high, to be quite honest, but in your home or in your office, it's closer to about 1 million particles per cubic foot of that size. So it's about 10 times better than when you're walking through the mine. Once you get into SNOLAB, that is actually 2,000 particles, bigger than half a micron in a cubic foot of air. So all of this work has to go into keeping all of the dirt and dust and everything from the mine outside, because it would ruin all of the experiments happening down there. So this is the kind of effort that SNOLAB goes through. So we got to the door in the last video. The first thing that you do when you get down there, you take off all your gear and you have a shower. So it is pretty convenient that you get to go to work and have a shower in the morning, particularly because the age is usually at about 6 a.m. So not a lot of time for a lot of hygiene before that. But then you come out of the shower and you get into special clean room gear. All of your clothes are down there provided for you, and you're into real clean room gear that you're going to be in for the rest of the day. And of course, in the evening, it's the opposite. Well, you don't have a shower, but you get rid of all your clean room gear. It gets washed underground and it's ready for you the next time or the next to next time. And you put your mine gear back on and you go back out through the mine. So not only do you have to wash yourself, all of the things, everything that you bring into SNOLAB has to be clean. So this is another video just with some bolts that are in what's called the car wash area. But in addition to those having to be cleaned when they get in, the car wash area also always has to be cleaned. Right through those doors at the end is the mine. So those 10 million cubic foot are fighting to come in through that door. And there's a bunch of really good staff at SNOLAB that are fighting to keep them out. And it's just a constant battle between those two. But it is another thing that when I used to give tours at SNOLAB, it would really stress, because it blows my mind that just pick something, pick the nut at the end of the bolt holding on that roll. That had to come underground and then be cleaned and then be installed. Everything has to come and be cleaned first before it's installed. So it's a huge effort that goes into this stuff. So I'll just talk for a little bit about the experiments at SNOLAB. This is a shot down the drift, the tunnel where one of the experiments is. There are dark matter experiments at SNOLAB, obviously. I've mentioned some of them. These are the PICO experiment here and the future site of the super CDMS experiment here. You may have seen the NEWS-G model outside in the foyer. The NEWS-G experiment is here. So there's a number of dark matter experiments that are going on, but it's not all that SNOLAB does. SNOLAB clearly has neutrino experiments. Anybody at Queen's, I think it's in your written code that you have to know about neutrino oscillations and things like that. That happened down here with the SNO experiment, which is now the SNO Plus experiment. There's other neutrino experiments. There's also technology experiments, just people doing things that would be better to be done underground. And another one I think is pretty cool is the biology experiments. There's a couple of different things that are going on with biology we can talk about later if you're interested. But SNOLAB is more than just dark matter, I guess, is what I'm stressing at here. So I've got a few more videos that they provided. This is a video of the PICO detector. These ports that are on the side are actually the cameras that I talked about earlier. The neat, pretty picture is inside there. And this is all contained inside a water tank. Not full, obviously. We don't fill them while the students are in them, usually. But these water tanks are there because although we've gotten rid of all of the backgrounds that came from the sky and all of that stuff, we still have other backgrounds that come from the walls and all that. We have to get rid of those as well. So putting your experiment in a water tank does a world of good in terms of trying to get rid of those. the Pico experiment. There's another one here. This is the CUTE experiment. It's one of the technology experiments where they're testing cryogenic detectors. It's because it's a nice test facility inside its own water tank. And then as we kind of come around the corner from CUTE, this platform is the future site of the Super CDMS experiment. So this is what exists of it so far, and it's just there ready and waiting for Super CDMS to come in and be installed on top of it. And again, you can see all of this stuff that's around, and just remember that everything had to come through that car wash and be cleaned by someone as it went in. So it's another thing that blows my mind. The final thing, there's a place called the Cube Hall, which is what we're looking at here. It's a very large room, several stories tall. We're going to kind of look over the edge and see a couple of different, again, some water tanks. This water tank is where the mini clean experiment used to be, and is where the next generation of the Pico experiment is going. As we pan to the side, we'll see the deep experiment. This is just the top of it, obviously. You can't see the water tank even because it's all covered up and installed. And if we could see over the edge and down about another story or so, you'd see the NEWS-G experiment, which is installed just on the floor at the bottom there. So I think that's it. Yeah, they just asked me to put up their coordinates, and then yeah, that's all I had. So thank you very much for listening.
Thank you, Ken. That was a really, really fascinating talk. And thank you to Snow Lab for providing a number of materials. I just want to grab my access to the online world so I can see any questions coming in that way. But I'm wondering, I think I will start there, but if anybody has a question here, then by all means raise your hand, and then I'll keep an eye out to see if there's anybody standing at the podium. Could we maybe stop sharing though so that we can see the podium?
And for our perimeter audience, you can make your way to the microphone again if you have questions.
Yeah, so let me just see. So Ken, there's a question for you from YouTube, which is how might you discern a dark matter particle from a neutrino interaction, for instance, or yeah.
Good question. So actually, that's a very pertinent question. One of the big issues that experiments are coming on is that as experiments get bigger and more sensitive, we're actually starting to be able to see some special kind of neutrino interactions. So it's true that it makes it that's one of the difficult things to tell apart, in fact. If we get down to the area where we're seeing a lot of these neutrino interactions, it's going to be problematic for trying to distinguish if there is a dark matter signal on top of it. There are things that people have proposed. One of the really neat ideas that has fallen maybe a tiny bit out of favor, but is that if you could actually, instead of just seeing that energy deposit, if you could find out where it's going, then you could do something like IceCube did. You could track backwards and see if they're all coming from the same direction. If that direction shifts throughout the year as we move around, there's a lot of different things you could do if we would be able to have the detection. Now, there are experiments that can do this. So far, they're very small. So maybe the next thing to do is to think about sizing up those experiments or finding a different way for existing experiments to be able to figure out which way that nucleus is actually moving. Oh, yeah. Yes.
We have another question in this room. Go ahead.
Hello. I have a question about the interaction of the dark matter with the matter in the sense. Mm-hmm. In the sense, you are considering that when a dark matter interacts with matter, would have a kind of a scattering, and this scattering would provide energy that would be found by the scintillator, or this scattering would cause like the phonon dispersion that would give it the signal to the scintillator?
So essentially what happens is that what we're expecting to see is that the dark matter particle comes in this scenario. Let's say that it happened. The dark matter particle comes in, it deposits that energy, and then some really complicated chemistry happens. But it's really the movement of the nucleus and the energy deposited from that scattering that causes the scintillation. So the dark matter particle itself has nothing to do other than causing that first recoil, the first movement of the nucleus. I think that was the question you're asking.
Yeah, and another question, because you are considering that the nucleus is moving, but in the sense that normally all the nucleus in the material is moving, and they have like this kind of quasi-particle known as phonon, that is the collective excitations of the particles inside of material, how this dark matter could interact with these phonons, in the sense that would be not interact with the nucleus, but with these movements of the particles.
So it's true that I have talked strictly about nuclear recoils. That's not necessarily the only way that we can detect we could potentially detect dark matter. It could be other things recoiling. It could be, for example, electron recoils. It could be a lot of things. But interacting with the kind of excitation in the atom itself is not generally one of the ways. You can create kind of virtual phonons through the vibrations that I talked about with the super CDMS detectors, that kind of thing. But that's the kind of the major way that you would be able to detect them that way. I hope that answers your question, but if not, I'm happy to talk to you again later.
I want to ask if there's any questions over at Perimeter.
We do
Anybody
have one
lined up at the microphone?
We have one question. Please go ahead.
I'm Brenna, and I have two questions. So the first one was about your shake method of discovering dark matter. You mentioned that you were going to be using a nucleus. What were the reasons, other than just that you could detect it, that you picked it? Could there be other materials that you could use?
So we look particularly for nuclear recoil, so for the movement of a nucleus, for a number of different reasons. Some of them being that since we don't know exactly how the dark matter interacts, how it actually, how it exchanges the energy, the nucleus gives us a really good situation in which there's a number of different ways it could exchange the energy. So in this, I'm kind of talking my way around using the spin of the nucleus versus the mass of the nucleus. If the dark matter kind of interacts with the mass of the nucleus, we want something big. So a nucleus is a coherent entity that is fairly big, has a lot of mass, so that gives us a big target. But a nucleus can also have an effective spin, which then if it interacts with spin, then we could actually use that instead. So there are a number of different ways. But as I said to this other question, looking for just the nucleus is not the only way. There are other ways. It just happens to be in the methods that I talked about, the way that we're doing it.
Mm-hmm. A little bit later on, or my second question is, when you were talking about the cold sensor that you were using for detecting dark matter, how much would it vibrate when dark matter passes through it?
Oh, yeah, great question. And it also gives me the chance to kind of wax not so poetic about these detectors. The way that these things work is absolutely amazing. Essentially what you have is you have a piece of metal on the top of it, which at this temperature is superconducting. And any small temperature change, we're talking into the kind of, millikelvin range, will actually cause that to transition from superconducting to non-superconducting. So in doing so, you're able to say that you had this very small temperature change. So a millikelvin is 1,000th of a degree Celsius, that you can detect that kind of level of change for this thing, which is another amazing thing about these detectors that I'm really glad you gave me the chance to rant about briefly.
Thank you so much.
Hello, thanks Dr. Clark and Dr. Mack for the talks. My name is also Katie, and I have a question in a couple of parts, but the main question is, how much dark matter is there, 1, in this room, 2, on this planet, and 3, in our solar system?
Wow, okay, this is some pretty good question. You're gonna try to make me do some math and remember some numbers right in front of you. So the number is 0.3 GeV per meter cubed, I think. So in this room, there is some energy. Now, how many dark matter particles are in this room, of course, depends on what the mass of each one of them. So we might know the kind of energy density of the particles in this room. And the same thing goes, unfortunately, for all scales. I'm going to cop out of all of them the same way. But we know the kind of energy density that's going on there. But what we don't know is how many particles that makes up. Because we need, there are a number of different ways we could do it. But we need some other way of being able to figure out just the mass of each particle individually to be able to say how many are here. Yeah, of course, as Professor Mack said in her talk earlier, there are ways that we can tell how much dark matter is in galaxies, right? We can see the spinning of these kind of things and that sort of thing. And I don't know the number for ours particularly. I apologize.
There's a question online I'd like to ask, which is underground at Snow Lab, what happens if someone has to like sneeze or cough? Do they have a special coughing area?
It would be pretty great if there was a special room that you had to go to every time you had to sneeze or cough. No, people go down there and you're able to, work normally, breathe normally, do all of that kind of thing. And you can still sneeze and do all of that stuff. Essentially, the reason that it's able to stay so clean is that there's a lot of air changes. We've all perhaps learned a little too much recently about circulation of air in rooms and that kind of thing. Snow Lab is particularly good in that the air in the entire lab is turned over very frequently and passed through filters. So if you come in and you sneeze, the product of your sneeze will be filtered out of the air quickly. And I apologize for having said that. I feel gross about it.
Maybe it is time for one last question over at Perimeter.
Yeah. So one of the things you mentioned that we're trying to detect here is if dark matter is bonking into a nucleus, right, and making that nucleus move a tiny little bit. That's dark matter interacting with regular matter, which, from what I heard before, I wouldn't have thought that was possible because dark matter doesn't have an electrical charge. So how does that work?
Right. So that's absolutely true. And it was, I think, described very well by Professor Mack in her talk. So it does not have an electrical charge. We know it doesn't interact electromagnetically. So in the same way that we think of things bonking into each other, like I said something about pool table and balls, it doesn't work that way. But in the same spirit, there are other ways to exchange energy. And so one of these is through the weak interactions. So instead of being something that exchanges photons that we're essentially doing every time we knock on things, you're going to exchange things like a W particle or a Z or something like that. So it's not the same. It's not the same way that we think of things interacting in kind of the macro world. In the atomic scale world, you can have different exchanges that aren't ruled out. And in fact, that weak interaction is the W in the weakly interacting massive particle that was mentioned earlier. So that's the interaction that we're looking for to happen, not the kind of usual electromagnetic interaction, but a weak interaction that happens there.
Thank you.
No problem.
All right, I think, is there one last question there? I think we do have time for just one more if you wanted to ask your question.
So I'm Violet, and my question was, has any success come out of any of the experiments so far?
Oh boy, the last question is the knife through my heart of my entire career spent doing this. No, that's a really good question. No, there has been no success so far. There have been maybe a few cases that thought that they might have seen something, but nothing has ever been backed up. So we can always look forward to the future when there will be success in these things, and we will be talking, maybe in the future dark matter days, we'll be talking about what it is rather than how we're trying to find it. But good question, even if slightly painful.
All right. I really do want to thank both Ken, and I want to thank Katie, and I want to thank the Snow Lab crew just for sharing all of their fascinating work here in the field of dark matter. Before we kind of announce a few other opportunities here in-house, I do want to basically sign off McDonald Institute from the feed and hand it back to our partners at Perimeter. Thank you.
Thanks, Mark. I want to thank Mark, Ken, and everyone who joined us in Kingston. Of course, we're also thankful to Katie here and to our audience in Waterloo and to everyone who has joined us online. It's been a pleasure to finally welcome back a live audience to Perimeter after such a long hiatus, and we hope to see all of you again soon.